Well, at this point in your career, you should have significant experience, as we say, in producing multi-view engineering drawings using the principles of orthographic projection. But if you're a normal student, at this point, you've probably worried a lot more about describing the shape of an object than you've worried about describing the size of the object. Well, in today's video, we want to get into this business of size description, or as we call it, dimensioning drawings. Before we're through today, we're going to talk about some of the basic terminology or the key words that relate to dimensioning drawings so that we will understand each other better. We'll cover some of the basic principles of good dimensioning, and along the way we'll point out some of the traps and pitfalls and the methods of poor dimensioning that you ought to stay away from. We'll also cover some basic hints that you can use in checking your dimension drawings to make sure that you have not either dimensioned something twice or left out important dimensions. And you might want to take a few notes and pay attention close, because there might be a quiz before we're through today. Well, let me turn to my video visual aid, that is my Amiga computer, to help present some of this basic terminology and information about dimensioning. Well, we have a lot of things to talk about, so let's get going here. Orthographic drawings, as you know, are used to communicate information about the shape of the object. And here's an interesting top view, front view, side view. We can tell pretty much everything about that object except the size. What we need to do is we need to add size information by adding dimensions to this drawing. And you're going to find out that before you're completely done with a drawing that the dimensioning will be more than half of your job. But the dimensioning includes all of the size information needed to manufacture the part. Now, to make sure that the dimensions on the drawings are as clear as possible, different folks have come up with different dimensioning standards, and we're going to follow the ones from the American National Standards Institute known as ANSI. As a matter of fact, the version of the ANSI standards we're going to follow is Y14.5M-1982, and the 1982 refers to the year that they most recently revised these standards. The practices that we're talking about apply to mechanical drawings, and if you're in the architectural drawing business or civil engineering or welding, there will be slightly different dimensioning practices. You also need to keep in mind that different companies use different dimensioning practices from time to time. But the ANSI standards, the American National Standards Institute standards, are pretty common. Well, we've got a lot of vocabulary, a lot of principles to cover. I'm going to turn up the speed here and talk pretty well as fast as I can. You have to listen as fast as you can, but you can't do this all in one setting. You're going to have to get your handouts from the instructors, your textbook, and review these rules after you've tried dimensioning some drawings of your own. But let's get going here. What is a dimension anyway? Well, a dimension is simply a numerical value that we use to show the size of an object or the feature, a particular feature on an object. And on our drawings, we assume the numerical values in the United States are in inches, unless there's a note someplace that says all dimensions are in millimeters, or unless there's a standard SI, System International symbol, that tells us it's a metric drawing. We assume inches, but in the U.S. we can use metric, but we need to specify in a note or in a symbol if it is a metrically dimensioned drawing. The dimension lines are thin, solid lines. They're all dark, by the way. They're not light and dark on drawings. They're all dark lines, but the object lines are thick. The dimension lines are thin, solid lines that are used to show the extent and the direction of a dimension. And we have extension lines that tell us exactly which part of the object the dimension refers to. They're drawn perpendicular, 90 degrees to the dimension lines, and they indicate which feature we're talking about. And on the end of the extension lines, on either end, we put arrowheads. And if you draw these arrowheads properly, you'll make them 1/3 as wide as they are long. My arrowheads on the computer screen are not the most beautiful because of limitations of the display here, but you'll make perfect 1/8 inch long, 1/3 as long, or 1/3 as wide as they are long arrowheads. Almost got that backwards, didn't I? 1/3 as wide as they are long if they're properly done arrowheads. No turkey tracks, please, when you do your arrowheads when you're dimensioning drawings. Take me to your leader line. If we have a note or something like this radius being dimensioned, we'll use a leader line with an arrow on the head that leads right to the feature that's being dimensioned. Leader lines are used for radius. Notice that this is different in the 82 standards than you might be used to or you might have seen in your book. Here we have the radius symbol preceding the numerical value nowadays. In the old days, they used to say 0.38R. Not anymore, not since '82. A leader line leads to a particular feature being dimensioned. Now, it turns out that every dimension on a drawing has to have a tolerance because there's no such thing as an exact dimension. And so what the tolerance means is the amount a dimension is allowed to vary. In this particular case, the diameter of this hole can vary anywhere from 0.625 to 620. You do some arithmetic, you find the tolerance is 0.005 of an inch. Here's a new thing for you. You might have seen this dimension as DIA. Not anymore. Latest standards say diameter symbol, this Greek letter preceding the numerical value for dimensioning diameters. More about that later. But the tolerances are the amounts that the dimensions are allowed to vary. And don't forget, every dimension on a drawing has a tolerance. Sometimes it's specified as upper and lower limits like this. Sometimes it'll be specified in the title block as a general note. But every number on a drawing must have a tolerance. Now, let's talk about the dimensioning principles. The overriding principle that governs all of these is that of clarity. We're trying to communicate size information as clear as possible. Sometimes these principles will appear to be conflicting. In that case, you don't flip a coin. You choose the way that you think is the clearest. Remember, the overriding principle is that of clarity. Now, when you dimension things, you should dimension every feature once and only once. We have a problem here. The height of this object is dimensioned 3 different ways. El Rongo, as they say. Notice that you can get the height directly from this overall dimension, or you can get it by adding up these dimensions, or you can get it by adding up these dimensions. That's wrong. We should only dimension the height one time because every one of these dimensions has a tolerance. Remember, suppose this is plus the tolerance. This is plus 2 tolerances overall if you add them up. This is only plus 1 tolerance, which is right. If this was 10 thousandths on each dimension tolerance, would this be 212 plus 10 thousandths? Would that be okay? Sure. Would 212 plus 20 thousandths, you had this and this, be okay? No, you got a conflict. You need to leave something out of here. Which ones you leave out depends on the next principle. You dimension the features, or you select your dimensions to suit the function of the features on the object. In this case, we decided that the height of this step was more important than the depth of this gap here, and so we leave this dimension out. In this case, we decided that the distance from the bottom of the block to the center of the hole is more important than the center to the top of the block, so we leave this one out. Now we have not violated the principle number 1. Each feature is dimensioned once and only once now, and we've selected them to suit the function of the object. At the beginning, you don't know the function of the object. You're going to have to guess, but as you get some more experience, you need to keep that in mind. Now, here's the principle that's most often violated by students, and that is the dimension should be placed in the most descriptive view of the feature being dimensioned. If you look at the side view and try to figure this out, look at the side view by itself, you don't know if that's an innie or an outie. You don't know if that thing's coming out at you or if it's a gap back in. That's not the most descriptive view of the height of that step. In the front view, you can tell that that is a step, and that's where you ought to put the dimension, in the most descriptive view of the feature. Don't forget that one. It's the most commonly violated principle. Dimensions should specify only the size of the feature, not the manufacturing process. In the old days, you saw this a lot on drawings, half-inch drill. Now, if the guy goes down to the shop and he finds he can make it cheaper by punching or getting one of them there laser things and zapping that hole, he's not allowed to do it. If you say drill on the drawing, he's got to drill. If there's a cheaper way, we ought to let him use it, so let's tell him what size to make it. Here again, the diameter symbol preceding the numerical value. Tell him what size. Don't tell him how to do his job unless you know it better. There may be a day that's important to tell him the manufacturing process, but if it's not important, don't do it. Now, the angles on the drawing, you don't want to go in here and dimension every one of these 90-degree angles. So the angles shown as right angles are assumed to be 90 degrees unless you specify it otherwise. If you wanted that to be 89.3, you'd have to dimension the angle. Otherwise, they're going to make it 90 degrees. Dimensions should be moved outside the boundaries of the object whenever possible. We're trying to promote clarity. You start filling up the object with dimensions. Pretty soon you can't tell the object from the dimensions. So the trick is to get them outside of the boundary lines of the object, if at all possible. Now that you might say someday it might be more clear to put it inside, but mostly it's not. Keep those dimensions outside of your boundaries as much as you can. Dimension lines should be aligned and grouped where possible to promote clarity and uniform appearance. Don't scatter them all over the place. Get a nice tidy place. That makes the machinist only have one place to look to get all these width dimensions. Now notice we flipped a coin to decide which one to leave out here. If we would have put the third dimension in here, we would have dimensioning the width twice. Now, we don't want to violate rule number 1. But group these dimensions, line them up, make it pretty, because sloppy is not as clear as clean and tidy. You should avoid the double crosses, okay? Avoid whenever possible this crossing thing. Notice the preferred way doesn't have any dimension lines crossing anything. I've got some instructor friends who would burn your drawing. They'd light a match to it if they saw you ever crossing a dimension line with an extension line. But avoid the double cross, okay? dimension, when you're dimensioning something, go from inside out. Don't start with the outside and then have to squeeze everything in here. You won't leave enough room. But dimension from inside out and avoid the double crosses. The space, by the way, the minimum space between the object and the first dimension line ought to be 3/8 of an inch. No less. You can make it more. You might have to make it more sometimes if you've got a lot of numbers to put in there and you need room. But don't make it any less than 3/8 of an inch. And the space between the dimensions ought to be at least 1/4 of an inch. Now sometimes when you fill this up with numbers, you got 1/8 inch high lettering in here, you got 1/8 inch high lettering here, 1/4 inch is not enough. It can be more, but don't make it any less than 1/4 of an inch or you'll be violating principle number 9. If you were in my class and I graded your dimensioning drawing, I'd say, oh, if you don't leave a visible gap right here, clear violation of principle number 10. There should be a visible gap between the object and the origin of the extension line, about a 32nd of an inch. But you need to have those gaps so you can tell where the object stops and the dimensioning starts. Those extension lines ought to dangle out here a nice uniform distance of about 1/8 of an inch. Don't make some of them 1/2 inch, some of them 3/4, some of them nothing, but put them all about 1/8 of an inch. Keep your drawing neat and tidy. Remember, you want to promote clarity, you keep the drawing neat. Hey, you get a bumper sticker that says, I break for arrowheads only if an extension line is coming close to crossing over an arrowhead. Then you put a little break in here to make room for your arrowhead. So, extension lines should be broken if they cross or are close to arrowheads. Now, when you're dimensioning circles or arcs, your leader lines, remember what a leader line is? Your leader line should be radial lines. What the heck does that mean? A radial line is one that if you followed it along for a ways, you'd hit the center of the circle. Now, you notice this leader line stops when it hits the circle, but if you lay your straight edge on there and follow this guy, you'll hit the center. If you follow this guy, it's a glancing blow. It misses the center. That's not a radial line. That's absolutely wrong. Dimension it with a leader line. That's a radial line. Dimension should be oriented to be read from the bottom of the drawing. In the old days, the old-fashioned days, when I was just a kid, we had what they called the aligned method. If you had a vertical dimension line, you'd twist this dimension around 90 degrees and line it up with the dimension line. Not anymore, not since the 82 standards. Now everything is oriented to read from the bottom of the drawing. No more twist the head to read half the dimensions. Unidirectional dimensioning is what we call it. And when you dimension diameters, once again, the 82 standards call for preceding the numerical value with the diameter symbol. It's diameter 0.50. No more 0.50 D period. That's no good anyway. D's tend to look like O's when you get bad copies and you get confused. DIA, hey, too much work. Learn the 1982 standard diameter symbol preceding the numerical value to dimension those diameters. Now, when you're dimensioning concentric circles, you should dimension them in the longitudinal view. You'll see a lot of example drawings where they put these dimensions right on top of here, all these circles, and if you put them all on this view, they'll be crisscross and it'll be confusing. So the new practices say, put them in the longitudinal view. Now, what if you don't have a section view? If you don't have a full section view, that center hole would be hidden, and that would violate rule number 3. You don't want to dimension to the least descriptive view. I claim that a hidden thing is always less descriptive than a visible thing. So what you do if that hole is hidden is you pull this one out and put it over in this view and you point to it with a leader line and you say diameter so-and-so with a radial line, of course. But that's the only case where you dimension concentric circles in the other than in the longitudinal view. Get them over here where the thing looks like the rectangular view and say diameter so-and-so, diameter so-and-so. And again, if the thing is hidden, don't violate rule number 3. That's a least descriptive view if it's hidden. Put it over there, but otherwise dimension concentric circles in the longitudinal view. When you're dimensioning a radius, again, put in a leader line and dimension it with a radius symbol, which is R, preceding the numerical value. Do you have to put a little plus sign in here? Sometimes. Not on this one, though, because this arc is tangent to 2 lines that are going to be dimensioned elsewhere. And we can find the center of this arc without locating it and putting dimensions to the center. However, in a little bit, I'll show you an example where we have to show where the center of the arc is. But in this case, the arc is tangent to both straight lines. We don't have to dimension to its center, but we do dimension radiuses with a radius symbol, R, preceding the numerical value. Now here's the case when you're dimensioning to a radius that you can't find the center without dimensions. Okay, you wouldn't know where to put that center line, and so in that case we put a little plus and we dimension with respect to the object, where to put the center of that radius or arc. In this case, we're dimensioning diameter and depth of holes that are counterbored. And when you're dimensioning holes that are counterbored or spot-spaced or countersunk, by the way, if you don't know those words yet, dig out your textbook and look at some pictures in the manufacturing processes section of your text to remind yourself or to learn what the difference between a countersink and a counterbore is. But in any case, when you're dimensioning this kind of thing, several holes, you can do it all in one note. Make this line radial again, but here we have diameter 3/8, 0.375. That's the little hole. That's the one that goes all the way through here. Then we have this strange symbol. This is the new ANSI symbol for counterbore. And this says counterbore diameter 1 1/8, 1.125. And that's this big diameter that does not go all the way through. Well, how deep does it go? We use the depth symbol here and the numerical value, 0.5 inches, 1/2 inch to show the depth of that counterbored hole. So now the machinist just has one place to look to find out everything about that whole system there. The diameter of the through hole, followed by the symbol that says what process to use. In this case, we want them to use a counterboring tool and make it 1 1/8. That goes to the depth of 1/2 inch. Now, sometimes on the books or in the books or on some of the old drawings, you'll see the words counterbore or abbreviated C-bore, or you'll see the words depth, and they're still very common. But we do have these symbols that you need to learn for dimensioning a system of holes in a note. Now, when we specify, here's a blind hole. That is, if you hold this hole up to the light, you can't see through. It doesn't go all the way through. When you specify the depth of a blind hole in a note like this, diameter 1 1/8, depth 0.5, 1/2. When you specify that, here's what it means. The 1/2 inch goes down the depth of the full 1 1/8 inch diameter. Now, you always have this little pointy drill point thing left over, but we're not talking about how deep that goes. We're talking about how deep does a 1 1/8 inch part of the hole go. When you're drawing this, by the way, you'll just take your 30/60 and you'll fake that in for the drill point. In reality, the angle on this drill point depends on what kind of stuff the drill was sharpened to drill. You sharpen a drill differently for wood than you would for cast iron. But when you specify the depth you're talking about is the depth of that full diameter. And the rest of this just dangles out. So depth of the blind hole, you need to know what that means. Now, there are 20 principles of good dimensioning, and if you remember all of those, you have a photographic memory, as I say. You need to go over this until you get them locked in. But remember, if you ever get to any of these principles, a situation where any of these principles seem to conflict, don't flip a coin, but use the overriding principle of dimensioning, and that is clarity. Well, I've presented 20 different principles of good dimensioning in a hurry, and it's going to be hard for you to remember all of those just from watching this tape one time. You may want to watch it a couple of times. Also presented a bunch of key words, some important terminology, and some hints along the way of things to watch out for when you're dimensioning. What you ought to have is a good reference. Here's one good reference. Hey, you didn't think you were going to watch these videos without a commercial, did you? Here's one reference that you could use. You could use the Engineering Drawing 100 workbook that goes along with our computer-assisted instruction materials. If you have the computer disc, by the way, there is a good chapter on dimensioning, and it'll give you on-computer practice and even some quizzes to practice your skills on dimensioning and your knowledge of the subject. But in addition to that, the workbook has a bunch of references that are very helpful. For example, on the back cover, we've copied the standard ANSI 1982 dimensioning symbols and tolerancing symbols. Inside the workbook, we have some other references. You can find a page in there with all those key words that we covered on the video, and also the 20 principles of good dimensioning are here. We also have some dimensioning tips and some hints for properly dimensioning a drawing, for locating dimensions. A lot of information is packed there on the reference pages in the workbook. Hey, earlier I promised you there might be a quiz. Were you taking notes? Are you ready for this quiz? Had my buddy Ferd Snodgrass prepare a drawing for us here, and we're going to use this for a quick quiz on dimensioning. Watch this. Had Ferd put letters in here instead of numbers just so we could follow it around and do this by the alphabet, A, B, C, D. But we're going to go through this, A, B, C, D, all these dimensions, and you're going to tell me if it's acceptably dimensioned or unacceptably dimensioned. What about dimension A? What do you think? Is that acceptable or unacceptable? Come on, you got to get involved now. You there in the next to the last row. What do you think? Acceptable or unacceptable? That's right, it's unacceptable. Why is it unacceptable? What is it dimensioning? What is dimension A for? It's locating that hole. Wait a minute, that's a hidden view of the hole. That's not very descriptive. Doesn't even look like a hole there. Dimension A, if you're going to put it in the most descriptive view of the feature being dimensioned, belongs in the top view. What about dimension B? Now we've got it in the top view, huh? Like that better. Oh, wait a minute. You say, what about this? Can you use a center line for an extension line? Yes. Should you make a gap there? No. You don't make gaps when you draw center lines across object lines. And what you do is just use that thin, solid center line as your extension line for that dimension. And B is all right. What about dimension C? Dimension the depth of this in the top view. Is that okay? Dimension the depth of an object in the top view? Sure. Why not? But if you're paying attention, you'll know there's a mistake with dimension C. Do you see the problem with C? Look at the extension line going across here. Nice visible gap between there and the object. No visible gap. -2, Ferd. You messed up on this one. You can't tell where the object stops and the extension line starts. Need a visible gap there. What about dimension D? Now we've got visible gaps. Hey, is this okay to put that number inside there and put the arrows outside? Yeah, sometimes like in F, you got a room for everything inside. You got a lot of space. But sometimes you have room for the arrows outside and the number inside. If it gets smaller than that, you might put the number and the arrows outside. But that's not what's wrong with D. There is something wrong with D, however. What is it? What's it dimensioning, really? This thing here, what is that thing? Is that a step up or a step down? Can't tell in the top view, can you? Belongs in a front view. That's the most descriptive view of the feature being dimensioned by D. What about E? Dimensioning this gap? Hey, is that a good descriptive view of the gap? Well, yeah, but hey, we got E buried down there almost in the body of the object. Let's put some extension lines up there. Get E up away from the body so we can tell what's the dimension and what's the object. And if you don't pay good attention to your line weights, you don't have your object lines twice as thick as your dimension lines and your extension lines, you won't know where the dimensions start and where the drawing stops. So get E out of there. What about, let's see, EF. Where's dimension F? Way up here. Overall width shows up in the top view. Looks okay? Yeah. At least several of my instructor friends don't like it there. They would say, hey, let's cluster all the width dimensions between the views and not scatter them all over the place. On a simple drawing like this, you might argue that that's not unclear, but some people would prefer to cluster width dimensions. F, G, what about dimension G? They must be telling us the diameter of that hole. Not where it's hidden. You violate rule number 3 again. Dimension the diameter of a hole where it looks like a hole. Don't dimension a diameter of a hole where it's hidden. G, H, what about dimension H? This radius here, huh? Does that look okay? Well, it's crossing E, but we're going to get E out of there, remember? Hey, is this one of those things where you need a little plus sign there, and you need to tell them where to put the center of that radius? Not on this one, because this arc is tangent to those lines there. And when the arc is tangent, you don't have to show the location of the center. You do that when the arc is not tangent to existing object lines. So H looks okay. What about I? I is the one people fight about. It's on the body here. Some people would get it off the body of the drawing and get it out of there. What about J? J is out of there. J is the height dimension in the front view. Not bad, except look out for the extension line here. It's dragging out too much. Take your erasing shield there, Ferd. Nip them all off equal so it looks nice and tidy. What about K? K is a height dimension. Some people don't like to scatter it out there, but there's something else wrong with dimension K. What is it? It's old-fashioned. In the old-fashioned days, we did this aligned method. We rotated vertical dimensions 90 degrees to read them from the side. Not anymore since '82. The unidirectional method is in. You need to rotate that back and make all the dimensions read from the bottom of the drawing. Well, had Ferd do this thing over again, and here's what he came up with. Clustered all these hole-related drawings up there together, so when the guy's doing the hole, the machinist, the guys or gals in the shop, are drilling this hole, they have one place to look for size and location of that. Dimension C, tidied that up. Dimension F, D, and E, all of these width dimensions are clustered here. Now one place to look for width, kind of grouped and kind of neat and tidy. H was in there, that was okay. What about this cluster of heights dimensions? Here's something you don't like. Some people don't want to drag that extension line across, this center line across those hidden lines. On the other hand, some people don't like to put the dimension I on the body of the drawing. And some people don't like to put it off here to the left where it's all alone and not in a good group. There's about 3 right answers to this. You don't like that, do you? You want it to be right or wrong. Sometimes you'll get into these situations where there's more than one right answer. But watch out, that doesn't mean there's only right answers. There's also more than one wrong answer. Now, if you get into an argument about with your friends about this dimension, whether it's right or wrong, And which principles am I violating? Remember, the overriding principle is that of clarity. And I think one could make a case that it's clear in this simple object, each of those three places. Well, you get everything dimensioned. There's one last thing you've got to do, and that's do the checking of the drawing. And here's a tip that my drafting supervisor back at Bell Labs when I was just 19 years old, first paying job. Here's one that he taught me that really works. When you get all done with the dimensioning, do this one last 2-minute check. Take your straight edge and just go left to right across the drawing, top and front views, and stop every time you come to a center line, a hidden line, a visible line, and say to yourself, self, did I dimension that feature? And scan this thing across all the views, left to right. And then turn around and scan this thing across all the views, top to bottom. Stop at every feature, make sure everything's dimensioned once and only once. And then there's one other last check that he did, and that is you take your scale and you lay it right on the drawing and you check every numerical value. If you don't do this, you're going to be embarrassed someday. The machinist is going to come up from the shop and he's going to say, you know that 2-inch block that you gave me to drill the hole in? He said, here it is, here's your block. And he gives you a handful of metal shavings, drops right there on your table because you didn't check and you forgot the decimal point on your 1/2 inch, and he says, here's that 5-inch hole drilled in that 2-inch block. Well, don't make mistakes like that. Go back and check your dimensions, and when you've done that, you will have described the size of the object as well as the shape of the object, and you will have a first-class engineering drawing if you follow the principles of good dimensioning.